Earth is a gravitational world, and any attempt to leave it forever begins with the simple fact that mass pulls. The ground, the oceans, the atmosphere, and the layer of satellites above them all sit inside Earth's gravitational field, which extends outward without a sharp boundary. The strength of this pull decreases with distance, but it never becomes exactly zero. For practical purposes, however, there are regions where Earth's gravity dominates motion, and regions where the Sun's gravity becomes the main influence. The time it really takes to leave Earth forever depends on which boundary is chosen the moment a spacecraft escapes Earth's direct gravitational binding, the moment it leaves the Earth-Moon system, or the moment it becomes so distant that Earth's pull is negligible compared with other forces. Each definition corresponds to a different distance and therefore a different time. The outermost constraint before engines and trajectories are considered is that leaving is not a single step. It is a path through layers of influence. At the surface, gravity is strong and the atmosphere adds resistance. At higher altitudes, the air thins and orbital motion becomes possible. Farther out, the Moon's gravity begins to matter. Beyond that, the combined Earth-Moon system gives way to solar gravity as the primary guide. The phrase "leave Earth forever" is therefore best understood as a progression through these layers, with each layer requiring energy and time. In the first layer, Earth's gravity sets the energy cost. A spacecraft on the surface is at a low gravitational potential relative to space. To move away permanently, it must gain enough energy to rise out of Earth's gravity well. In simple terms, the spacecraft must increase its speed so that Earth cannot pull it back. The minimum speed to escape from Earth if there were no atmosphere and no further engine burns is called escape velocity. It depends on Earth's mass and on the distance from Earth's center at which escape is attempted. From the surface, escape velocity is a little over 11 kilometers per second. This value is not a cruising speed that must be maintained forever. It is a threshold in energy. If a spacecraft has that speed at the surface and no further forces act, it would slow as it climbs, converting kinetic energy into gravitational potential energy, and it would asymptotically approach zero speed at infinite distance. In reality, launches do not achieve escape velocity straight from the ground, and they do not ignore the atmosphere. They also do not travel in straight radial lines because orbital mechanics makes it more efficient to build speed along a near horizontal path, once above most of the atmosphere. The practical process therefore begins with reaching a stable orbit. Orbit is a state of continuous freefall around Earth, where the sideways speed is high enough that as the craft falls, Earth curves away beneath it. In low Earth orbit, typical speeds are close to 8 kilometers per second. This is less than escape velocity, which is why a satellite in low Earth orbit is still gravitationally bound to Earth. If its engine stops, it continues to circle Earth rather than drifting away. To leave forever, it must add additional speed to transition from a bound orbit to an escape trajectory. In that sense, the time to leave Earth forever includes at least two phases: the time to reach orbit and the time to depart from orbit onto a path that will not return. The first phase has a fairly fixed timescale for chemical rockets. From ignition to orbit insertion, the ascent typically lasts on the order of several minutes. Exact values differ by vehicle and trajectory, but the overall picture is stable. The craft rises through dense air, accelerates rapidly, and stages to drop empty tanks. The atmosphere is crossed quickly because drag increases sharply with speed in dense air, and because gravity losses accumulate if the craft climbs too slowly. The goal is to gain altitude and sideways speed efficiently. The timing is constrained by physics and by the limits of materials and engines. Even if the destination is not orbit but a direct escape path, the early minutes look similar because the craft must still pass through the same atmospheric and gravitational environment. After the main burn ends, an upper stage may coast and then burn again, to circularize orbit depending on the mission design. This adds additional time, often tens of minutes from launch, to a stable parking orbit for missions that will later depart. This parking orbit is a waiting room allowing the vehicle to coast to a favorable position for the departure burn. Here the concept of time becomes more nuanced. Leaving Earth forever is not always immediate after reaching orbit. Mission planners choose when to perform the escape burn based on the desired direction and on the positions of Earth, the Moon, and the target. If a spacecraft is heading toward the Moon, it performs a burn when it is at the correct point in its orbit, to place its trajectory on a path that intersects the Moon's orbit. If it is heading to another planet, it performs a burn at a time that aligns its departure with the direction needed to match the desired heliocentric transfer orbit. This means that the time between reaching low Earth orbit and executing the escape burn can range from minutes to hours, and in some missions it can be longer if multiple orbits are used for checkout or if constraints require waiting. Yet the physical act of leaving in terms of escaping Earth's gravitational binding depends primarily on that burn. Once a spacecraft increases its speed beyond the local escape threshold at its orbital altitude, its path relative to Earth becomes a hyperbola, an open curve that does not close back on itself. It will recede from Earth, slowing as it climbs away. The distance from Earth at which it is considered to have escaped depends on the definition used, but in energy terms, the escape condition is already met at the moment after the burn when the craft's total energy relative to Earth becomes positive. This creates a useful distinction between leaving as a dynamical state and leaving as a geographical distance. Dynamically, the craft is no longer bound as soon as its trajectory becomes unbound. Geographically, it is still near Earth for some time as it climbs outward. A practical boundary used in mission analysis is the sphere of influence, a region around Earth within which Earth's gravity dominates the craft's motion relative to the Sun. The sphere of influence is not a physical boundary. It is an approximation that simplifies calculations. Its radius is on the order of hundreds of thousands of kilometers, comparable to the distance to the Moon. Another related concept is the Hill sphere, the region where Earth can retain satellites against solar tides. This region is also on the order of 1,000,000 kilometers. Leaving the Hill sphere means that the Sun's gravity dominates and Earth can no longer hold the craft as a satellite in the long term. The time to cross these regions depends on the departure speed. A typical departure toward interplanetary space might have an excess speed relative to Earth of a few kilometers per second beyond the escape threshold. With such a speed, a craft can travel from Earth to lunar distance in a few days, and it can pass beyond the sphere of influence in a similar timescale. This suggests a simple answer. If leaving Earth forever means becoming unbound from Earth, it happens within hours of launch once the escape burn is performed. If it means travelling beyond the Earth-Moon system so that Earth's gravity is no longer the primary influence, it takes days. If it means reaching distances where Earth's pull is negligible, it takes weeks to months depending on speed. These are still only the gravitational layers. The atmosphere adds another constraint because it prevents a gentle departure. The craft must fight drag and heating, and it must carry propellant to do so. Chemical rockets are limited by the energy per unit mass in chemical bonds. Because the required speed change is large, the rocket equation makes the mass of propellant dominate. Most of the launch mass is fuel, and only a small fraction becomes the payload that reaches orbit or escape. This is why leaving Earth is hard. The time may be minutes to orbit and days to leave the system, but the difficulty lies in energy and mass, not in duration. The phrase "really take" therefore points to the fact that quick departure does not mean easy departure. Even a direct escape mission requires a vehicle capable of delivering the necessary speed changes, and such vehicles are large and complex. The next inward layer will clarify what leaving Earth actually means in terms of being bound or unbound, separating orbit from escape, and explaining how definitions change the answer, because without that clarity, time estimates can be misunderstood as either too short or too long. Leaving Earth forever depends first on what is meant by leaving, because a spacecraft can depart the ground and still remain tied to Earth by gravity in several distinct ways. The inward move here is from Earth as a gravitational world to the definitions that separate temporary separation from permanent departure. The simplest case is a high-altitude aircraft. It leaves the surface, but it remains supported by air and remains deeply within Earth's gravity field. A little higher, a spacecraft can pass above most of the atmosphere on a suborbital arc. It rises coasts and falls back. This is leaving the ground, but it is not leaving Earth in a lasting dynamical sense. The craft remains on a trajectory whose total energy relative to Earth is negative. Gravity slows the ascent, reverses the motion, and returns the craft. Even if the craft reaches space by some altitude definition, it is still bound. This shows that altitude alone is not the key. The key is whether the path is bound or unbound. A bound path repeats or returns. An unbound path does not. A stable orbit is the next major category. In orbit, a spacecraft is above most of the atmosphere and can remain there for long periods. Yet it is still leaving only in the sense of distance from the surface. The spacecraft remains gravitationally bound to Earth. Its speed and altitude correspond to an energy state that allows it to circle Earth rather than fall to the surface immediately, but it does not have enough energy to escape. In a simplified view, without air drag and other perturbations, an orbit repeats endlessly. In reality, low orbits slowly decay due to atmospheric drag, and higher orbits can be perturbed by Earth's non-uniform gravity and by lunar and solar tides, but the essential point remains: orbit is a bound relationship. The craft remains a satellite of Earth. If leaving Earth forever means never returning and never remaining a satellite, then merely reaching orbit is not sufficient. The craft must change its energy state so that Earth can no longer keep it as a satellite. This is why escape is a separate concept. Escape is not defined by being far away. It is defined by having enough energy relative to Earth that the trajectory is open. In orbital mechanics, the sign of the specific orbital energy determines whether the path is bound. Negative energy corresponds to elliptical or circular orbits. Zero energy corresponds to a parabolic trajectory that is just at the threshold of escape. Positive energy corresponds to a hyperbolic trajectory that escapes. These are idealized categories, but they provide a clean definition. Under this definition, leaving Earth forever occurs at the moment the spacecraft's trajectory becomes hyperbolic relative to Earth. That moment can occur near Earth, often from a parking orbit. It is triggered by a propulsion burn that adds speed in the direction of motion, increasing kinetic energy. After this burn, the spacecraft still remains physically close to Earth for some time because it must climb away, and because its speed relative to Earth decreases as it trades kinetic energy for gravitational potential energy. Yet the dynamical status has changed. In the absence of later intervention, the craft will not return. It will recede to very large distance. This definition makes leaving Earth forever a question of energy rather than of distance, and it often yields a surprisingly short time in the sense that the decisive step can occur within hours of launch. However, there are reasons why some discussions use distance-based definitions instead. In practice, the sphere of Earth's dominance is not infinite. Far away, the Sun's gravity becomes more important than Earth's. A spacecraft that is unbound from Earth still remains within the Earth-Moon system for days, and its path is influenced by both Earth and Moon until it passes beyond the region where Earth's gravity is the main factor in determining its motion around the Sun. Therefore, another definition of leaving Earth forever is leaving the Earth-Moon system in a dynamical sense, becoming primarily a heliocentric object. Under this definition, the boundary is not the escape condition, but the crossing of a region where Earth's influence is small compared with the Sun's. This region can be described approximately by the Hill sphere. Inside the Hill sphere, Earth can retain satellites against solar tidal forces. Outside it, Earth cannot hold a stable satellite orbit in the long term. A spacecraft leaving Earth on a hyperbolic path will usually pass through the Hill sphere boundary on the order of days to perhaps a couple of weeks depending on its excess speed. This gives a longer but still modest timescale compared with human intuition of leaving forever. Another definition is even more practical. Leaving Earth forever means leaving any realistic possibility of return with the propulsion available. In that sense, the trajectory and the mission plan matter. A craft could be on an escape trajectory but still carry enough propellant to perform a braking maneuver and return at least in principle. Many interplanetary missions are designed with no plan for return, but that does not mean return is physically impossible in all cases. A craft can execute course corrections that alter its path, and it could even be redirected toward Earth if mission goals changed and if propellant margins allowed. Therefore, leaving forever can mean leaving with no intention or capability of return. This is not a purely gravitational definition. It combines physics with engineering and mission design. Under this definition, leaving forever is more connected to the total available speed change, not just the escape condition. A mission that uses a minimal escape trajectory with limited propellant margin may pass a point of no return after a certain time, when the remaining propellant is insufficient to reverse the path. This point may occur soon after the escape burn, but it can also be planned later. For example, a spacecraft can be sent toward the Moon, first use a gravitational assist to shape its departure, and then depart the Earth-Moon system. In such a case, the mission remains in a regime where Earth return might be feasible, until after the lunar encounter, after which the path and remaining resources may make return unrealistic. This adds days to the timescale. There is also the atmospheric and safety definition. Leaving Earth forever could be understood as leaving the atmosphere and remaining above it permanently. Under this definition, reaching orbit qualifies, but so would any high enough stable orbit. Yet this is a weak definition because it conflates long-term orbiting with true departure. A satellite in orbit can remain for years, but it is still Earth-bound. It also remains within a region where debris, atmospheric drag, and orbital perturbations matter. In addition, the orbital environment is not isolated. Over very long times, the Moon and the Sun can perturb orbits, and radiation pressure can matter for small objects. But for most practical discussion, orbiting is not leaving forever. It is staying near Earth in a different mode. A more expansive definition would treat leaving Earth forever as leaving the entire neighbourhood in which Earth remains relevant as a gravitational guide. This would push the boundary farther outward, perhaps to distances where Earth's gravitational acceleration becomes much smaller than the acceleration from the Sun, and where navigation and dynamics are dominated by heliocentric motion. This is not a sharp distance, but it provides a sense of scale. At a few million kilometers, Earth's pull becomes very weak compared with solar gravity, and a spacecraft's orbit around the Sun becomes the main story. Under a typical interplanetary departure, such distances can be reached in weeks. This means that depending on the chosen definition, the timescale can range from hours to weeks. The differences are not contradictions, they reflect the layered nature of the gravitational environment. The spacecraft's status changes first in energy, then in dominance of gravitational influence, and finally in practical irrelevance of Earth's pull. Another factor in defining leaving forever is the role of trajectories that use low thrust. Not all spacecraft leave using a single decisive burn. Electric propulsion systems can provide continuous low thrust over months, gradually raising orbit and then departing. In such cases, the moment of becoming unbound may occur later, after many spirals outward rather than shortly after launch. The craft can spend weeks or months in the Earth neighborhood before it finally reaches escape energy. This changes the time to leave forever under the energy definition. It also shows that propulsion type is a crucial context. Chemical rockets tend to produce short, intense burns, making the escape transition abrupt. Low-thrust propulsion makes it gradual. Therefore, any claim about time must specify the propulsion regime or at least assume the common chemical launch plus escape burn pattern. A realistic summary at this layer is that leaving Earth forever has a physical threshold escape that can be crossed quickly, but the meaning of forever can be tied to broader boundaries like the Hill sphere, or to practical mission constraints stretching the timeline from hours to days or longer, depending on trajectory design. The next inward step will focus on the plain meaning of escape velocity itself, not as a speed to be held forever, but as an energy condition, and it will show how the escape requirement changes with altitude and with the path taken, because those details determine how quickly the threshold can be crossed and how much propulsion is actually needed. Escape velocity is often described as the speed needed to leave Earth, but its plain meaning is an energy threshold that depends on where the spacecraft starts and on how it travels. The inward move here is from definitions of leaving to the specific physical requirement that marks the transition from bound to unbound motion. In a simple model with no atmosphere and no additional forces, a spacecraft launched from Earth's surface with a speed of a little over 11 kilometers per second would be at escape velocity. As it climbs, gravity would slow it, converting kinetic energy into gravitational potential energy. If the initial speed were exactly the escape threshold, the craft would approach infinite distance with speed approaching zero. If the initial speed were greater, the craft would still slow as it climbs but would retain some excess speed at large distance. If the initial speed were less, it would reach a maximum distance and fall back. This gives escape velocity a clear interpretation. It is the boundary between trajectories that return and trajectories that do not in a two-body approximation. Yet the real departure does not occur as a straight upward shot from the surface. It occurs through orbital motion, where building sideways speed is more efficient once above most of the atmosphere. This is because orbital energy depends on both speed and altitude, and because a spacecraft in orbit already has most of the required speed in the sideways direction. The difference between orbital speed and escape speed at the same altitude is smaller than the difference between surface rest and surface escape. This means that the extra speed needed to go from a low Earth orbit to escape is only a few kilometers per second, not 11. The launch still requires the large effort of getting to orbit, but the escape step from orbit is a comparatively smaller addition. The escape requirement changes with altitude because gravitational potential energy depends on distance from Earth's center. Farther out, Earth's gravity is weaker, and the escape speed from that point is lower. This does not mean that reaching high altitude is an easy alternative because gaining altitude itself requires energy. But it means that the escape condition can be met in different ways by increasing speed at low altitude by raising the orbit, and then increasing speed or by a combination. In practice, chemical launch vehicles take a payload to a parking orbit. From there, an upper stage or the spacecraft itself performs a burn to raise speed and place the craft on an unbound trajectory. The amount of speed change required depends on the desired hyperbolic excess velocity. The speed relative to Earth the craft will have far away after it escapes. A mission heading to another planet needs not only to escape Earth but also to achieve a specific heliocentric orbit that intersects the target. The required hyperbolic excess speed depends on the target and on timing. For a departure to Mars or Venus, the required excess speed is modest. For departure to the outer planets, it is larger. For a mission intended to leave the solar system, it can be larger still. Yet for the specific question of leaving Earth forever, the minimal condition is just to have zero or positive energy relative to Earth which corresponds to an excess speed of 0 or above. In a parking orbit around a few hundred kilometers altitude, orbital speed is near 8 kilometers per second. Escape speed at that altitude is a little over 10 kilometers per second. The difference is a bit more than 3 kilometers per second, which is a common scale for an escape burn. But this simplified subtraction hides important details. The burn is performed at a specific point in orbit and the trajectory is shaped to achieve the desired departure direction. The escape burn is most efficient when performed near perigee, the lowest point of the orbit, because adding speed there increases the energy of the orbit most effectively. This is an expression of the Oberth effect, where thrust applied at high speed produces a larger change in orbital energy than the same thrust applied at low speed. The effect is not mysterious. It arises because kinetic energy depends on the square of speed. A small increase in speed at an already high speed adds more energy than the same increase at low speed. Therefore, many departure plans use a low parking orbit to maximize the benefit of the burn. This reduces propellant requirements for a given departure energy. It also influences time. If a spacecraft is already in a parking orbit, it may wait until it reaches the correct perigee point aligned with the departure direction, then execute a burn lasting minutes. After that, it is on its way. This means that in the chemical rocket regime, the decisive energy transition is usually concentrated in a short time window, even though the travel outward takes longer. Another nuance is that escape velocity is defined relative to Earth alone, but in the real solar system, the Moon and the Sun are present. The Moon's gravity can assist departure. A spacecraft can be sent on a trajectory that passes near the Moon, where the Moon's gravity changes the spacecraft's velocity relative to Earth. Depending on geometry, this can increase or decrease the spacecraft's energy relative to Earth. This is one reason lunar flybys can be used to shape departure paths. The Sun's gravity also matters. A spacecraft leaving Earth is already in orbit around the Sun because Earth itself orbits the Sun at about 30 kilometers per second. In heliocentric terms, an Earth escape trajectory is a modification of Earth's orbital motion. The spacecraft's heliocentric speed after departure is Earth's orbital speed plus or minus the departure velocity relative to Earth depending on direction. This is why a spacecraft can leave Earth and still remain bound to the solar system. Leaving Earth forever does not mean leaving the Sun. It means detaching from Earth as the primary central body. The escape condition relative to Earth is only the first threshold in a sequence. The question asks how long it would really take. In the context of escape velocity, the time to meet the threshold depends on how quickly the spacecraft can add the required energy. For chemical propulsion, the time is short minutes for the escape burn once in orbit. The longer time is not in reaching the threshold, but in the prerequisite steps launch to orbit checkout and alignment. The total from launch to Earth escape injection is often on the order of hours depending on mission design. Some missions reach parking orbit, then perform an escape burn on the first orbit, which can be within about an hour to 2 hours. Others may remain in orbit longer for checks or due to window constraints. Yet the burn itself remains short. For low-thrust propulsion, the time changes. An electric propulsion spacecraft might begin in a high orbit or geostationary transfer orbit and then spend weeks raising apogee, gradually increasing orbital energy. It can spiral outward, performing many small thrust arcs. It becomes unbound only after accumulating enough energy. In such a case, the time to cross the escape threshold can be weeks or months. This is still leaving Earth forever, but the path is gradual. The trade is fuel efficiency versus time. Low-thrust systems have high exhaust velocities and can achieve large total speed changes with less propellant, but their thrust is low, so the acceleration is small and the maneuver takes long. Therefore, a realistic answer about time must specify the propulsion and the trajectory strategy. In common public imagination, leaving Earth forever is associated with a large rocket launch. Under that common chemical scenario, the time to escape Earth's gravitational binding is typically within a few hours of launch. Under alternative low-thrust scenarios, it can be much longer. After the threshold is crossed, the outward travel remains. The spacecraft does not instantly become far away. It takes time to reach the Moon's distance and to pass beyond Earth's dominant region. That travel time depends on excess speed. With an excess speed of a few kilometers per second, lunar distance is reached in a few days. Beyond that, the craft becomes primarily heliocentric. Therefore, the escape velocity concept provides the physical marker of permanent departure, but it is only the first marker. The next inward step will examine the practical limits of rockets, especially chemical rockets, because while the escape condition can be described cleanly, achieving it requires delivering a large speed change through propulsion systems whose constraints dominate mission architecture, and those constraints influence not only feasibility, but also the timing of how quickly a spacecraft can proceed from surface to orbit to escape. The time to leave Earth forever is shaped less by the clock and more by the limits of propulsion, because the propulsion system determines how quickly energy can be added and how much mass must be carried to do it. The inward move here is from the escape requirement to the technology that meets it, focusing on chemical rockets, because they remain the main method for leaving Earth's surface. A chemical rocket produces thrust by expelling hot gas at high speed. The gas comes from chemical reactions between fuel and oxidizer. In the vacuum of space, there is no air to supply oxygen, so the rocket must carry both. This is the first reason rockets are massive. They must carry not only payload and structure, but also the chemicals that generate thrust. The second reason is the rocket equation. To change speed by a certain amount, the rocket must expel propellant. The larger the required speed change, the larger the fraction of the initial mass that must be propellant. Because leaving Earth requires a large total speed change, the propellant fraction becomes very high. This is why most of a launch vehicle's mass is fuel and oxidizer, and why stages are used. Staging allows empty tanks and engines to be dropped, reducing mass and improving efficiency for the remaining propulsion. From the perspective of time, chemical rockets have high thrust. They can accelerate strongly and thus complete the major speed changes in minutes. This makes the departure timeline short in terms of propulsion duration. Yet the mass and staging requirements impose practical constraints. A rocket cannot accelerate at full thrust from the first moment without overwhelming structural limits and without producing excessive aerodynamic loads in the dense lower atmosphere. It must throttle and shape its ascent. It must also manage heating and vibration. Therefore, the ascent profile is optimized to balance gravity losses, drag losses, and structural constraints. Gravity loss is the cost of fighting gravity while not yet having enough sideways speed. Drag loss is the cost of pushing through air. Both add to the required speed change. Even if escape velocity from the surface is a little over 11 kilometers per second, the rocket must provide more than that in total, because it loses energy to drag and to gravity while climbing. Reaching low Earth orbit typically requires a total speed change on the order of 9 to 10 kilometers per second, when losses are included, even though orbital speed itself is about 8 kilometers per second. This means that even a mission that does not need to orbit, but aims for a suborbital arc, still pays a significant penalty if it attempts to climb too steeply through the atmosphere. This is why practical trajectories build horizontal speed. The time to orbit, therefore, is constrained by the need to pass through the atmosphere quickly while building speed efficiently. Typical ascent times of several minutes are not arbitrary. They reflect engine performance staging events and the balance of losses. An upper stage may then complete orbit insertion after a coast. This coast allows the vehicle to reach a desired point in its trajectory, often near apogee, before burning to raise perigee and make the orbit stable. This adds tens of minutes. For missions that will depart Earth, the vehicle often uses a parking orbit first. This is partly because the launch window for a particular interplanetary direction may not align perfectly with the moment of reaching orbital speed. It is also because a parking orbit allows checks and timing. The escape burn can then be performed at a specific point to achieve the desired departure direction in inertial space. Depending on mission design, the escape burn can occur on the first orbit, which means within about an hour or two of launch, or it can occur after several orbits, which can extend the time to several hours. Some missions use an upper stage that performs the escape burn immediately after reaching a suborbital trajectory without a stable orbit, effectively performing a direct injection. This can reduce the time from launch to escape injection, but it requires precise targeting and leaves less margin for checks. It also means that if something goes wrong, the mission cannot easily be recovered into orbit. Therefore, many missions choose the parking orbit approach. The high thrust of chemical stages means that the escape burn itself remains short, often minutes. The longer time is spent in coast and alignment, not in thrust. The limitations of chemical propulsion also explain why leaving Earth forever is usually planned as a single decisive impulse rather than as a slow continuous climb. Chemical rockets are efficient at producing large thrust for short periods. They are less efficient in terms of propellant usage than electric propulsion, but their thrust makes them practical for launch and for escape burns. Electric propulsion, by contrast, can achieve high exhaust velocity, meaning it uses propellant more efficiently for a given speed change, but its thrust is low. An electric propulsion spacecraft cannot lift off from Earth because it cannot overcome gravity and atmospheric drag at the surface. It must be delivered to space by a chemical rocket. Once in space, it can use electric thrust to gradually raise orbit and potentially escape. The time becomes long. It can take weeks to raise from low Earth orbit to a higher orbit and longer to escape. Some missions begin in a high elliptical orbit delivered by a launcher, reducing the time needed for electric propulsion to reach escape. Even then, the timeline is measured in weeks or months rather than hours. This shows a fundamental trade. If the question is how long it takes in calendar time, chemical departure is faster. If the question is how much propellant is needed, electric propulsion can be more efficient. In most cases of leaving Earth forever, the initial departure uses chemical propulsion for speed. Within chemical launch limits, the rocket equation also shapes payload capability. A launcher that can deliver a payload to low Earth orbit may deliver much less payload to escape because the additional speed change requires additional propellant in the upper stage. This affects mission planning. If the payload is large, the mission may require multiple launches, assembly in orbit, or staging beyond Earth orbit. These strategies can extend the time between first launch and actual escape because assembly and preparation take time. For robotic probes, this is less common because they are designed to fit within a single launch. For human missions, especially permanent departure scenarios, mass becomes much larger because life support shielding, habitat volume and redundancy add mass. This pushes toward complex architectures that can significantly extend the time to leave Earth forever in a practical sense, not because of physics but because of logistics. If leaving Earth forever involves building and fueling a large spacecraft in orbit, the calendar time could be months or years of preparation, even if the final departure burn takes minutes. Therefore, there is a difference between the physical travel time and the operational mission time. The physical travel time from launch to escape injection can be hours for chemical departure. The operational time to execute a permanent human departure could be far longer due to assembly and testing. There is also the question of trajectory shaping. A spacecraft can depart Earth with a direct burn, but it can also use gravity assists. A gravity assist uses the motion and gravity of a body such as the Moon to change a spacecraft's velocity relative to Earth or the Sun without using propellant. In the Earth neighborhood, the Moon is the main assist partner. A lunar flyby can alter the departure direction and energy. This can allow a mission to reach a desired heliocentric orbit with slightly less propellant or with a different launch window. But a lunar flyby adds time because it takes days to reach the Moon. Therefore, if the goal is to leave Earth quickly, a direct escape burn from parking orbit is faster. If the goal is to reduce propellant requirements or to reach specific energy targets using the Moon, can be beneficial. This introduces another trade between time and energy. Chemical propulsion also imposes constraints on safety and reliability. High-thrust ascent is intense, the atmosphere is unforgiving, launch opportunities are constrained by weather range, safety and technical readiness. These factors do not change the physics of leaving Earth, but they affect the real calendar time to execute a mission. A craft may be ready to leave in principle, but a launch may be delayed for days or weeks. Therefore, the phrase "really take" can be interpreted in operational terms as well as in purely dynamical terms. Yet within the constraints of the role here, the focus remains on the physical timeline. Once launch occurs, and within that framing, chemical propulsion compresses the main energy additions into minutes and hours. The craft can be unbound from Earth within hours of launch. The craft can be beyond the Earth-Moon system in days. The difficulty is not duration, but the mass and energy required to achieve the speed changes. The next inward step will track the specific time and energy sequence from launch pad to low Earth orbit, because even though the ascent is short, it contains the major energetic hurdle, and understanding its stages clarifies why leaving Earth forever often begins with orbit as a deliberate intermediate step, rather than with a single continuous climb to escape. From the launch pad to low Earth orbit, the timeline is short, but the energy change is large, and this phase determines whether leaving Earth forever is even possible because it provides the baseline speed and altitude from which escape can be reached efficiently. The path begins at rest on the surface where the vehicle is held against gravity and surrounded by dense air. At this point, the spacecraft has essentially no orbital energy. It shares Earth's rotation, which provides some sideways speed, but relative to the speed needed for orbit, this contribution is modest. The first minutes after ignition are therefore dominated by a single task to increase speed rapidly while moving upward through an atmosphere that becomes thinner with altitude. A chemical rocket achieves this by producing high thrust, meaning it expels mass at high speed and generates a reaction force. The vehicle's acceleration is not constant. It changes as propellant is consumed, as stages separate, and as engines throttle to control aerodynamic loads. Even so, the overall shape of the ascent remains similar across many launch systems because the same physical constraints apply. The vehicle rises vertically at first, partly to clear the launch site and partly because the dense lower atmosphere makes it inefficient to build very high horizontal speed immediately. As it climbs, it begins a gradual pitch program that tips the trajectory down, range building, horizontal velocity while continuing to gain altitude. This shift is essential because a stable orbit is primarily a matter of sideways speed. Altitude provides time to avoid the atmosphere, but without the right horizontal speed, the vehicle falls back. During the earliest portion of ascent, aerodynamic pressure increases as speed rises while air is still dense. This region is often near the maximum dynamic pressure, a point where the combination of air density and velocity produces the highest load on the vehicle. To pass through this region safely, engines may throttle down briefly, reducing acceleration and thus reducing aerodynamic stress. This introduces a small time increase, but prevents structural failure and reduces risk. At the same time, gravity is continuously pulling downward. Any time spent thrusting without adding useful horizontal speed contributes to gravity losses, which are a real part of the energy budget. The ascent profile therefore seeks a balance. It climbs fast enough to reduce time in dense air and limit drag losses, but not so fast or at such a steep angle that gravity losses become excessive. As the vehicle rises, the atmosphere thins, drag drops, and the trajectory becomes more dominated by orbital mechanics rather than by aerodynamics. Stage separation is a key event in this phase. A multi-stage rocket carries a large first stage that provides thrust while also lifting the mass of upper stages and payload. As the first stage burns propellant, it becomes lighter, but once its propellant is depleted, it becomes dead mass. At that moment, separating it improves performance because the remaining stages no longer have to accelerate empty tanks and engines. The first stage often operates for only a few minutes. After separation, the second stage ignites or continues firing, operating at higher altitude where air is thin and where the engine nozzle can expand exhaust more efficiently. The upper stage, therefore, tends to have better performance in terms of effective exhaust velocity. It continues adding speed and raising the trajectory. During this period, the vehicle's path is often a long arc that carries it downrange with altitude rising toward a peak. If the mission is to reach a stable low orbit, the vehicle must ensure that after engine cut off the lowest point of the path, the perigee remains above the atmosphere. If perigee dips into the atmosphere, drag quickly removes energy and the orbit decays. Therefore, the ascent is designed so that the final burn places the vehicle on a trajectory that is either already circular enough to avoid significant drag, or is followed by a later burn to raise perigee. Many missions use a parking orbit strategy. The vehicle reaches an initial orbit that is safe and stable enough for a period of time, allowing systems checks and enabling a later departure burn. The time to reach this parking orbit includes powered flight and sometimes a coast. Powered flight from liftoff to main engine cutoff typically occurs within minutes. After cutoff, the vehicle may coast to a more favorable point for orbit insertion. For example, if the vehicle reaches a high point in its trajectory while still on a suborbital path, it can coast and then perform a short burn near that high point to raise perigee and close the orbit. This coast can last tens of minutes. The purpose is to use propellant efficiently and to shape the orbit precisely. During coasting, the vehicle is already in freefall following a trajectory determined by its current velocity and Earth's gravity. The engines are silent, but the mission is still in progress. The final orbit insertion burn is usually short compared with the ascent, often minutes or less, because the orbit shaping requires a precise adjustment rather than a long continuous climb. Once this burn is complete, the spacecraft or upper stage is in low Earth orbit, moving at roughly orbital speed and circling Earth. The physical meaning of arriving in low orbit is that the vehicle now has a large amount of kinetic energy and is above most of the atmosphere. It's still deep in Earth's gravity well, but it is in a state where leaving Earth forever becomes a smaller incremental step. The craft can now add a few more kilometers per second to escape rather than having to supply the full escape energy from rest at the surface. This is why low Earth orbit is such a common staging point. It converts the problem of leaving Earth from a single huge step into a sequence of steps that can be managed by staging, by mission timing, and by careful navigation. The time to reach low Earth orbit measured from liftoff is therefore relatively short in a physical sense. It is on the order of less than an hour for most missions, and often much less, though exact timing depends on the specific vehicle, the target orbit altitude and inclination, and whether a coast is used before orbit insertion. What matters more than the exact minutes is the structure of the sequence. First comes the ascent through dense air, where the vehicle must limit drag and heating. Next comes the period where horizontal speed is built and altitude continues to rise. Then comes the final shaping into a stable orbit. Each step is constrained by the need to manage losses. Drag loss comes from air resistance, which converts some of the rocket's energy into heat in the air and on the vehicle. Gravity loss comes from the fact that thrust must counter gravity during ascent, and any thrust that does not contribute to orbital energy is effectively spent just holding up against gravity. Steering loss comes from the fact that thrust is not always perfectly aligned with the velocity vector, especially during turns and attitude control, which reduces the efficiency of energy addition. These losses mean the vehicle must provide more total speed change than the orbital speed itself. The overall speed change requirement to reach orbit, including losses, is substantial, and this requirement is what makes leaving Earth difficult, even though it can be fast in time. Once in orbit, the vehicle is in continuous freefall and experiences microgravity conditions, yet the vehicle is not free of constraints. Even at a few hundred kilometers altitude, thin traces of atmosphere remain and can cause gradual drag. The vehicle must also contend with Earth's uneven gravity field, which can perturb the orbit over time, and with gravitational influences from the Moon and the Sun. For most near-term operations, these effects are small compared with the effect of propulsion burns, but they matter over weeks and months. A parking orbit is therefore not a permanent state unless station keeping is performed. For a mission that will leave Earth forever, the parking orbit is typically a temporary phase. The departure burn is planned soon after orbit insertion, often within a few hours, because remaining longer can require additional management and can expose the vehicle to orbital debris risk. The timing of the departure burn depends on geometry. If the goal is to depart in a certain direction relative to the Sun, the burn must occur when the spacecraft's orbital position aligns with that direction. This can require waiting for the spacecraft to move along its orbit to the correct point. Because a low Earth orbit period is on the order of roughly an hour and a half, opportunities recur frequently. This means that the waiting time to reach the correct burn point is often limited to a few orbits, which corresponds to a few hours. This is a key reason why leaving Earth forever, in the sense of becoming unbound, can occur quickly after launch. The vehicle reaches orbit coasts as needed, and then executes a burn at a favourable point to achieve escape energy and the desired departure vector. Yet in some mission architectures, reaching low Earth orbit is not followed immediately by departure. If the spacecraft is large, or if it requires assembly, low Earth orbit becomes a construction site rather than a staging point. Components may be launched separately and docked. Fuel may be delivered and transferred. Systems may be checked over longer periods. In such cases, the physical time from the first launch to the moment of departure can be months, even though each individual ascent to orbit still takes less than an hour. This distinction matters for the phrase "really take." In pure orbital mechanics, the decisive changes happen quickly. In operational reality, the time can be dominated by preparation. However, if the focus remains on a single vehicle departing directly low, Earth orbit insertion compresses the main difficulty into minutes of powered flight and a short period of coasting and orbit shaping. After that, the spacecraft is poised at the edge of a new category of motion, where a comparatively short additional burn can remove Earth as the central body. The next inward step will follow that transition, examining how a spacecraft leaves orbit behind by adding the additional speed required for an escape trajectory, and why the departure is usually executed from a specific point in orbit. Because the details of that burn and its timing set the immediate timeline for becoming unbound and begin the outward drift that makes Earth's pull gradually less important. Leaving orbit behind is the moment when departure becomes permanent in the strict dynamical sense, because a spacecraft transitions from a repeating bound path to an open path that will not return unless new propulsion is applied. The inward move here is from reaching low Earth orbit to the specific sequence that converts orbit into escape. In low Earth orbit, the spacecraft is moving fast, and Earth's gravity provides the centripetal pull that keeps it circling. Its total energy relative to Earth is negative, meaning it is bound. To leave forever under the energy definition, it must raise its total energy to 0 or above. In practical terms, this is done by performing a burn that increases the spacecraft's speed along its direction of motion, because adding speed in the direction of travel increases orbital energy most efficiently. The burn is usually performed at or near the lowest point of the orbit where speed is highest, because this maximizes the effect of the burn on the trajectory's energy. This is a practical expression of the Oberth effect. If the goal is to depart Earth quickly, the mission uses a low parking orbit, executes the burn at a planned time, and immediately begins to recede from Earth on a hyperbolic trajectory. The burn itself may last several minutes if performed by an upper stage, or it may be shorter or longer depending on engine thrust and the required speed change. Yet compared with the days that follow, the burn is brief. The result of the burn is often described as an injection. It injects the spacecraft into a new orbit class. If the burn is insufficient, the spacecraft may enter a high elliptical orbit rather than escape with an apogee far from Earth but still bound. If the burn meets the escape condition, the spacecraft's path relative to Earth becomes a hyperbola. In that case, the spacecraft passes a point called perigee, near where the burn occurs, and then climbs outward. Its speed decreases as it climbs, but it never reaches a turning point. It continues outward indefinitely. The degree to which it continues outward quickly depends on the hyperbolic excess speed, the speed it retains at large distance relative to Earth. This excess is not the speed near Earth, which may be 10 kilometers per second or more. It is the residual speed far from Earth after the gravitational slowdown. A small excess speed means the spacecraft climbs away slowly after leaving Earth's immediate neighborhood. A larger excess speed means it departs more quickly. Interplanetary missions typically have an excess speed of a few kilometers per second. That is enough to reach lunar distance in days and to move beyond Earth's dominant region within similar times. The timing of the injection burn is set by geometry. A spacecraft departing Earth does not simply want to escape. It wants to escape in a particular direction relative to the Sun, so that its heliocentric orbit matches the target. Earth is orbiting the Sun at about 30 kilometers per second. The spacecraft inherits that motion. Its departure burn adds a velocity relative to Earth that changes the heliocentric velocity. If the spacecraft departs in the same direction as Earth's motion, it gains heliocentric speed and moves to a higher orbit around the Sun, potentially reaching outer planets. If it departs opposite Earth's motion, it reduces heliocentric speed and moves inward toward the Sun, potentially reaching Venus or Mercury. Departing in other directions changes inclination and other orbital elements. Therefore, the burn must occur when the spacecraft's position and the desired departure vector align. This is why a parking orbit is used. The spacecraft can wait in orbit until it reaches the correct point in its path to execute the burn in the desired direction. Because the spacecraft circles Earth in roughly an hour and a half, alignment opportunities recur frequently. This means that once in orbit, the time to reach a suitable injection point is often limited to a few hours. For missions that require very specific launch windows relative to the target planet, the launch itself is timed so that the injection burn can occur promptly. This reduces the time spent in orbit and simplifies mission operations. In some cases, the injection is performed by the upper stage shortly after reaching orbit, before the stage's propellant boils off, or before battery and thermal limits become restrictive. The choice affects the real timeline. A direct injection architecture might reach orbit and then burn within minutes, making the time from liftoff to escape injection less than 2 hours. A more cautious architecture might wait for checks, extending it to several hours. Either way, in the chemical regime, the time scale is still short compared with the days of outbound travel. After injection, the spacecraft enters the outbound coast. It is still close enough to Earth that Earth's gravity dominates its motion. It follows a path that can be described as a hyperbola relative to Earth. In this region, mission control typically performs tracking and may conduct small correction burns to refine the trajectory. These corrections are usually small compared with the injection burn, but they matter because tiny angular errors near Earth can translate into large misses far away. The outbound trajectory is sensitive. This is especially true for missions aiming for lunar flybys or planetary encounters. Therefore, the early hours and days after injection often include careful navigation. Yet these corrections do not change the basic fact of escape. The craft is already unbound. It is now a traveller through a region where the moon's gravity can also influence the path. If the trajectory crosses near the moon can bend it significantly. If the trajectory is far from the moon's effect is smaller but still present as a perturbation. The time to reach the moon's distance from Earth is often a few days for typical trajectories, though. Faster trajectories are possible with higher excess speed. For a minimum energy lunar transfer, the time can be several days. For higher energy, it can be shorter. For a direct escape toward interplanetary space, the trajectory may pass near lunar distance, but not necessarily near the moon's location. Still, lunar distance provides a useful scale for judging how far the craft has gone. Within a day, the craft can be hundreds of thousands of kilometers away if its excess speed is high, but if excess speed is low, it may take longer. As the craft passes beyond the region where Earth dominates, its motion becomes more naturally described as an orbit around the Sun with a small perturbation from Earth. This transition is not instantaneous, but for many mission analyses it can be approximated by crossing a sphere of influence boundary. Inside this region, Earth-centered coordinates are used for navigation planning. Outside heliocentric coordinates are used. The time to cross this boundary depends on the departure energy and on the direction relative to the Sun. With typical interplanetary excess speeds, it can be on the order of days. This means that if leaving Earth forever is defined as becoming primarily heliocentric, the time from launch to that state is often a matter of a few days. If leaving forever is defined more strictly as becoming unbound from Earth, it happens earlier at injection within hours. This distinction remains central. The burn is the key event. The coast is the gradual transition. In some trajectories, the spacecraft does not depart Earth directly, but uses an intermediate orbit and then performs a burn at apogee far from Earth to escape. This can reduce certain requirements or fit mission constraints, but it changes timing. The spacecraft might spend days in a high elliptical orbit before escaping. Similarly, a low-thrust spacecraft might take weeks. Yet in the common case, the time to leave orbit behind is measured in hours after launch, and the time to move beyond Earth's dominant region is measured in days. The sense in which it takes longer is tied to the gradual nature of distance. Earth's pull becomes weaker steadily, not suddenly. Even after the craft is unbound, Earth still accelerates it slightly, and it continues to slow relative to Earth as it climbs. This can feel counterintuitive because leaving forever sounds like a dramatic crossing of a boundary. In reality, it is an energy transition followed by a long, gentle drift outward, punctuated by occasional corrections and influenced by the moon. The next inward step will focus on the moon's role more directly because the moon is the nearest significant gravitational partner and can strongly shape departure paths and timelines, especially for missions that use lunar flybys to alter energy or direction. And understanding that influence clarifies why some departures take days and why some trajectories can be designed to be slower or faster depending on how they use the Earth-Moon system. The Moon is the first major gravitational partner encountered after Earth, and it can turn a simple idea of escape into a more complex but often more efficient sequence because its gravity can reshape trajectories, change timing, and reduce propellant needs for certain goals. The inward move here is from the orbit to escape transition to the role of the nearby companion body that shares Earth's neighbourhood. The Moon orbits Earth at a distance of a few 100,000 kilometers, and its gravity is strong enough to measurably deflect the path of a spacecraft that passes near it. In the Earth-Moon system, A departing spacecraft does not move under Earth's gravity alone. It moves in a three-body environment where Earth and Moon both pull while the Sun provides a steady background influence. This means that trajectories can be designed to take advantage of natural gravitational flows. A spacecraft can leave a parking orbit and head toward the Moon on a translunar trajectory. Depending on timing and geometry, it can approach the Moon and then be deflected. In the Earth-centered frame, the Moon can add or subtract energy from the spacecraft's Earth relative motion. In the heliocentric frame, the Moon's motion around Earth and Earth's motion around the Sun both matter. The practical outcome is that a lunar flyby can rotate the spacecraft's velocity vector and can change its speed relative to Earth. This can be used to reach destinations that would otherwise require a larger propulsion burn. The cost is time. A flyby requires travelling out to lunar distance, which takes days. Therefore, when asking how long it would really take to leave Earth forever, the presence of the Moon introduces a choice between faster direct injection and slower but potentially more efficient multi-step departures. A direct departure from low Earth orbit to interplanetary space can make the spacecraft unbound from Earth within hours and put it on a heliocentric path quickly. A departure that uses the Moon may keep the spacecraft in the Earth-Moon system for several days before it truly becomes a heliocentric traveller, because the spacecraft must first reach the Moon and then depart after the flyby. In some cases, missions may loop around Earth and Moon multiple times using repeated encounters or resonance orbits to gradually change energy. These complex trajectories can take weeks or months. They are used when propellant is limited, or when a mission uses low thrust and wants to exploit gravitational dynamics. Such trajectories show that leaving Earth forever is not always the fastest path. It can be engineered as a slow drift through the boundary regions of gravitational influence. One reason the Moon is useful is that it provides a way to change direction without burning propellant. A spacecraft leaving Earth for a planet needs a specific departure direction in heliocentric space. Achieving that direction purely by propulsion can require a larger speed change if the initial orbit plane or launch site constraints limit the departure geometry. A lunar flyby can rotate the plane of the trajectory and can adjust the direction of the outbound path relative to the Sun. This can be especially useful for missions that need high inclination relative to Earth's orbital plane, or for missions that require a specific departure asymptote. It can also be used to set up a trajectory that returns near Earth later, for an Earth gravity assist building up energy over multiple passes. In the context of leaving Earth forever, the Moon is therefore not simply an obstacle or a destination. It is a tool that shapes the path. The Moon also affects the definition of leaving. A spacecraft that is unbound from Earth may still pass near the Moon and experience a significant deflection. In such a case, the spacecraft's path relative to Earth can change, but if it is already unbound, the Moon does not necessarily make it bound again. It can, however, change the hyperbolic excess speed relative to Earth, either increasing it or decreasing it. A decrease could slow the spacecraft's departure, making it spend longer in Earth's neighbourhood. An increase could speed up the departure and help it leave the Hill sphere more quickly. Therefore, even for direct departures, the Moon's position at the time of departure can influence the detailed outbound path. Mission planners model this. They choose injection times and directions that avoid unwanted close approaches or that exploit beneficial ones. The timescale remains on the order of days for lunar distance interactions, but the specific trajectory can change the time to reach the boundary, where Earth's influence is secondary. A more subtle role of the Moon involves the existence of weak stability boundary trajectories. These are paths where a spacecraft uses very little energy relative to Earth to drift outward and be captured or released under the combined gravitational influence of Earth, Moon and Sun. Such trajectories can be used for transfers to the Moon that require low propulsion, but they take longer than direct transfers. In some cases, a spacecraft can depart Earth on a trajectory that slowly meanders toward the Moon over weeks. The same kinds of dynamics can be used for leaving Earth's gravitational influence gradually. This is an example of how the term "really take" can vary dramatically depending on the choice of trajectory. A direct chemical injection might leave Earth's dominance in days. A weak stability boundary path might take weeks or months. Both can satisfy the condition of eventual permanent departure, but they differ in timing and energy. For human missions, the choice of trajectory has additional constraints. Longer transfers expose crews to more radiation and require more life support supplies. Therefore, human departures generally favour shorter times, even at higher energy cost. Robotic missions can accept longer times if it saves propellant or enables mission objectives. This difference matters in the concept of leaving Earth forever. A robotic probe can take a slow path and still be successful. A crude one-way mission would be limited by biology and by the need for reliable systems over time. The Moon also sets the scale for the Earth-Moon system boundary discussion. Many practical definitions of leaving Earth forever use lunar distance as a milestone. When a spacecraft reaches the distance of the Moon and continues outward, it's clearly beyond the near-Earth environment. Yet it can still remain within Earth's Hill sphere. Therefore, lunar distance is a useful but not definitive boundary. It is a marker of leaving the immediate neighbourhood, not of leaving Earth's long-term gravitational reach. Nevertheless, in operational terms, reaching lunar distance often corresponds to a shift in navigation strategy and in communications delay. Signals now take more than a second to travel one way, and the spacecraft is far enough that Earth orbit debris concerns are irrelevant. The craft's trajectory becomes dominated by the planned interplanetary path. This is often what people mean when they imagine leaving. In that sense, the Moon distance is a psychological boundary. It marks the transition from near-Earth operations to deep space operations. It occurs in days, not in minutes. The influence of the Moon also introduces timing windows. For a lunar flyby, the Moon must be in the right position at the time the spacecraft arrives. This constrains the departure time from Earth orbit. If the spacecraft launches into parking orbit and then waits for a translunar injection window, it might wait hours or perhaps a day depending on constraints. This adds to the total time. For interplanetary missions that do not intend to fly by the Moon, the Moon's position still matters to avoid collisions or close approaches that could alter the trajectory unexpectedly. Therefore, the Moon is part of the scheduling problem. Earth departure is not just about the Sun-target alignment, but also about the Moon's orbital phase and the geometry of the Earth-Moon system. In practice, these constraints are manageable, but they can influence the decision to inject on the first orbit or after several orbits. All of these considerations lead to a clearer understanding of time. Under a direct chemical departure, the spacecraft can be unbound from Earth within hours and can cross lunar distance within a few days. Under a departure that uses the Moon intentionally reaching a definitive state of being primarily heliocentric, may take longer, often several days and sometimes much longer, for low-energy or multi-loop trajectories. In both cases, the Moon is the main driver of complexity within the first several 100,000 kilometers. Beyond that, the Earth-Moon system itself becomes a single unit in the gravitational landscape dominated by the Sun. The next inward step will therefore move from the Moon's influence to the boundaries of the Earth-Moon system in a more formal sense, describing where Earth's dominance fades and solar gravity takes over, and how that transition can be characterized through concepts like the Hill sphere and practical spheres of influence, because this provides a more precise timescale for when leaving Earth forever becomes leaving Earth's system rather than just escaping Earth's gravity in the strict two-body sense. The boundary of the Earth-Moon system is not a line in space but a gradual shift in which gravity dominates, and describing that shift provides a practical timescale for when a departing spacecraft stops being mainly an Earth-centered traveler and becomes mainly a Sun-centered traveler. The inward move here is from the Moon's local influence to the larger structure of the Earth-Moon gravitational domain. In a strict physical sense, Earth's gravity extends indefinitely, but in orbital dynamics the influence of a body is often described relative to another body. Near Earth, Earth's gravity dominates the motion of a spacecraft. Far away, the Sun's gravity dominates. Between these there is a region where both matter and where the combined Earth-Moon system behaves as the secondary influence within the Sun's larger field. Two commonly used concepts describe this region. One is the sphere of influence, a radius derived from the relative masses of Earth and the Sun, and the distance between them used as an approximation to determine where Earth-centered calculations are adequate. The other is the Hill sphere, derived from the balance of gravitational attraction and tidal forces, representing the region where Earth can retain satellites in the presence of the Sun's pull. The Hill sphere is often the more physically meaningful for long-term stability. Its radius is on the order of about 1.5 million kilometers. The sphere of influence is of similar order, but somewhat smaller depending on the definition used. These are both much larger than low Earth orbit and larger than the Moon's orbital distance, which is why a spacecraft can pass the Moon and still be within Earth's broader gravitational dominance. To leave Earth forever, in the sense of leaving the Earth-Moon system, a spacecraft must travel to distances on the order of 1 million kilometers or more. How long that takes depends on its hyperbolic excess speed relative to Earth. After an escape injection, the spacecraft's speed relative to Earth decreases as it climbs. The rate of outward motion is not constant. It is faster near Earth, slower as it approaches the far region where gravitational potential energy increases. If the excess speed is small, the spacecraft may drift outward gradually. If the excess speed is larger, it passes through the boundary more quickly. A useful way to think about the time is to consider typical interplanetary departures. A spacecraft leaving Earth for another planet usually has a hyperbolic excess speed of a few kilometers per second. This means that far away from Earth, its relative speed remains on the order of that excess. Near Earth, it is higher. With such a departure, travelling 1 million kilometers can take on the order of several days to perhaps a couple of weeks, depending on trajectory, geometry, and excess speed. A rough estimate can be made by imagining an average outbound speed of a few kilometers per second. At 2 kilometers per second, travelling 1 million kilometers would take about 500,000 seconds, which is a bit under 6 days. At 3 kilometers per second, it would take under 4 days. But the actual speed is not constant and the path may not be radial. Therefore, the timescale is often several days. This aligns with the experience of deep space missions, where within a week after launch a spacecraft can be well beyond the Moon and be clearly in deep space operations with Earth's influence treated as a perturbation on a heliocentric trajectory. This provides a practical answer for leaving Earth's system days, not months, for common chemical departures. Yet there are important caveats. First, the departure direction relative to the Sun matters. The Hill sphere is not spherical in the strict sense because the gravitational environment is shaped by the Sun's tidal field. The region of stability is elongated and depends on direction, with different distances to the effective boundary toward and away from the Sun. The Lagrange points locations where gravitational and rotational effects balance in a rotating frame sit near the edges of this domain. The points labelled L1 and L2 lie roughly along the line connecting Earth and the Sun, at distances of about 1.5 million kilometers from Earth. Spacecraft placed near these points, such as certain observatories, are not leaving Earth's system forever. They remain in a region where Earth and Sun forces balance in a way that allows relatively stable orbits around the Lagrange points. This illustrates again that being far away is not the same as being unbound. A spacecraft can be 1.5 million kilometers away and still be in a stable configuration related to Earth. Therefore, leaving the Earth-Moon system can be defined in multiple ways even at this boundary. One can define it as crossing beyond the Hill sphere, so that Earth can no longer hold the spacecraft in any long-term orbit. Under that definition, a spacecraft on a hyperbolic escape path will cross that boundary and will not be retainable by Earth without intervention. Another can define it as simply moving beyond the practical sphere of influence used for mission design, where heliocentric dynamics dominate and Earth-centered equations are no longer the natural frame. Under that definition, the transition can occur slightly earlier. In both cases, the time is in the range of days for typical departures. Second, the trajectory can be shaped to linger. A spacecraft can be launched into a high elliptical orbit with an apogee near the boundary, and then perform burns at apogee or perigee to slowly adjust energy. It can also be placed into resonant orbits with the Moon that keep it in the Earth-Moon domain for extended periods. These are not typical for simple interplanetary probes, but they exist and are used in certain mission designs. Under such designs, the time to leave the Earth-Moon domain can be weeks or months. Third low-thrust spacecraft can take far longer. If a spacecraft uses electric propulsion to spiral outward, it may take months to reach the vicinity of 1 million kilometers and to accumulate enough energy to escape. In that case, the boundary crossing is not a rapid coast after a short burn, but the endpoint of a long, gradual climb. This again shows that the time depends on propulsion regime. For a human mission aiming to leave Earth forever, time inside the Earth-Moon boundary could be constrained by life support and radiation. Long lingering trajectories would be undesirable. The likely design would therefore aim for a quick transit through the boundary, meaning a high-energy departure and a timeline of days. For robotic missions, the design can tolerate long times if needed for propellant efficiency. Therefore, when speaking of how long it really takes, one must decide whether the question is about the physical minimum under typical high-thrust departure or about the range across plausible mission types. The boundary framework clarifies that leaving Earth forever in a system sense is not achieved the moment a spacecraft becomes unbound. It is achieved when Earth is no longer the primary dynamical influence. That occurs after the spacecraft has travelled to distances comparable to the Hill sphere. This takes days for common interplanetary departures. It also clarifies that Earth can remain relevant even at those distances through stable Lagrange point orbits, which are not permanent departure. Therefore, leaving Earth forever in the sense of being on a path away from Earth implies both being unbound and not choosing to remain in a Lagrange region. A spacecraft bound to an Earth-Sun Lagrange orbit is in a deep space environment but is not leaving Earth forever. It remains in a relationship maintained by gravitational balance and occasional station keeping. In contrast, a spacecraft on a hyperbolic escape from Earth is leaving. This is a distinction between deep space location and deep space departure. Once the spacecraft is mainly heliocentric, Earth becomes a small perturbation. Navigation planning uses the Sun as the central body. The spacecraft's speed relative to Earth can still change due to the geometry of the heliocentric orbit and due to subsequent encounters, but the primary dynamical framework is now solar. At this point, leaving Earth forever becomes less about Earth and more about what the spacecraft is leaving next. A craft that is heliocentric is still bound to the solar system unless it has enough heliocentric energy to escape the Sun. Many missions do not. They leave Earth but remain within the solar system. If the phrase forever is interpreted as never returning to Earth that can be satisfied by a heliocentric orbit that does not intersect Earth again, even if it remains bound to the Sun. Therefore, crossing the Earth-Moon boundary is often the most relevant physical milestone for the idea of leaving Earth forever. Yet the question can also be extended to leaving the Sun's domain, which is a different and larger problem. The next inward step will therefore move from the Earth-Moon boundaries to the next barrier, solar gravity, clarifying that leaving Earth forever often still leaves a spacecraft inside the solar system, and that truly departing into interstellar space requires additional energy and a much longer timescale of travel, because the definition of forever can expand from Earth to the broader gravitational home of the Sun. Leaving Earth forever usually means leaving Earth as a central body, but the spacecraft almost always remains bound to the Sun, and this changes the meaning of travel time because the next gravitational home is vastly larger than the Earth-Moon system. The inward move here is from the Earth-Moon boundary to solar gravity, as the dominant framework of motion once Earth is left behind. Earth itself moves around the Sun at roughly 30 kilometers per second, and any spacecraft departing Earth begins with that inherited heliocentric motion. The spacecraft's departure from Earth adds or subtracts a few kilometers per second in heliocentric terms depending on departure direction. This means that most spacecraft, even those that escape Earth easily, are still on heliocentric orbits that remain within the solar system. They may travel to other planets, to the outer solar system, or to distant reservoirs of small bodies, but they remain gravitationally bound, unless their heliocentric speed is high enough to exceed the Sun's escape speed at their distance from the Sun. This is a much larger threshold than Earth escape. It is also a different type of question. Earth escape can be achieved within hours of launch and leads to leaving Earth's region in days. Solar escape, if it occurs, is usually not achieved by a simple departure burn alone. It often requires additional boosts from planetary gravity assists or a very energetic launch. Even then, the spacecraft must still travel for years before it reaches distances where it is clearly outside the main planetary region. This shows that the phrase "leave Earth forever" can mean two different things. It can mean leaving Earth and becoming heliocentric, which is a days-scale milestone, or it can be interpreted as leaving the solar system entirely, which is a decade-scale travel story and a much higher energy requirement. The Sun's gravity is deep because of the Sun's mass. At Earth's distance, the escape speed from the Sun is about 42 kilometers per second. Earth's orbital speed is about 30 kilometers per second. Therefore, to escape the Sun from Earth's orbit, an object would need an additional heliocentric speed of roughly 12 kilometers per second in the most favorable direction, neglecting details of orbital mechanics and energy. But because a spacecraft cannot easily add that much speed directly, missions often rely on gravity assists. A gravity assist uses a planet's motion around the Sun. When a spacecraft flies by a planet, it can exchange energy and momentum with the planet in the heliocentric frame. The planet's orbit changes imperceptibly, and the spacecraft's orbit can change significantly. By chaining assists, a spacecraft can build up heliocentric energy. This is how some probes have reached high speeds and departed the main planetary region. Yet even after reaching solar escape, the spacecraft's speed relative to the Sun is not extremely high compared with interstellar distances. It might be on the order of tens of kilometers per second. At such speeds, covering the distance to the nearest stars still takes tens of thousands of years. Therefore, leaving the solar system is not the same as reaching another star. It is a long coasting process through interstellar space. For the question at hand, the key is that Earth forever and solar system forever are not the same. A spacecraft can leave Earth forever and still remain in a solar orbit that crosses Earth's path again. That would be a temporary departure in terms of Earth, because later it could encounter Earth again. To ensure never returning, the spacecraft's heliocentric orbit must avoid Earth's orbit. This can be done by departing to an orbit with a different semi-major axis or inclination. A mission to Mars naturally does this. It moves to an orbit that crosses Mars's orbit. Depending on timing and mission design, it might still cross Earth's orbit in the future, but navigation can be planned to avoid Earth encounters. A mission to the outer planets moves to a larger orbit and does not return to Earth unless course corrections are made. Therefore, leaving Earth forever is usually satisfied by becoming heliocentric on a trajectory that does not intersect Earth again and that can happen quickly. The time to achieve that in this chemical departure regime remains hours to escape Earth and days to leave the Earth-Moon domain. The longer times appear when discussing the consequences of being heliocentric. Travel to other planets takes months or years depending on distance and trajectory. Travel to the edge of the solar system takes decades for current spacecraft speeds. Therefore, the phrase "really take" can be answered at multiple scales. There is also an important physical distinction between leaving by speed and leaving by energy. A spacecraft might not need to be unbound from the Sun to be considered leaving Earth forever. It only needs to avoid Earth return. That requires a change in heliocentric orbital elements which can be achieved with modest additional speed relative to Earth depending on direction. The deep energy well of the Sun makes full escape costly, but leaving Earth's vicinity is comparatively cheap once the craft is in orbit. This is why interplanetary missions are feasible with current technology. They do not need to escape the Sun, they need only to change orbit around the Sun. In this sense, leaving Earth forever is closer to stepping out of one room into a corridor that connects to many other rooms, rather than leaving the building. The building is the Sun's domain. The corridor is heliocentric space. The step from Earth to heliocentric space is achievable quickly. The step from the Sun to interstellar space is far more demanding and does not change the immediate fact of leaving Earth. The time to leave the solar system can also be defined in multiple ways. One can define it as reaching the heliopause, a region where the solar wind pressure balances the pressure of the interstellar medium. This is not a gravitational boundary but a plasma boundary. It lies at a distance of roughly 100 astronomical units, though it can vary with solar activity and direction. Reaching this region at speeds of tens of kilometers per second takes decades. Some spacecraft have reached and crossed it. This provides a reference for what leaving the solar system might mean in a physical environment sense. Yet in gravitational terms, the Sun's influence extends much farther and small bodies in distant reservoirs remain bound at tens of thousands of astronomical units. Therefore, solar escape is an energy condition while leaving the solar wind bubble is an environmental condition. Both are different from leaving Earth. The question of how long to leave Earth forever is best answered by keeping the scale focused on Earth. Once a spacecraft is unbound from Earth and beyond the Hill sphere, it is effectively gone from Earth's system, that is days. But if the phrase forever is interpreted emotionally as never coming back and disappearing into deep space, people may imagine a far longer journey. In that case, the journey is governed by heliocentric motion and by the distances involved. The spacecraft's speed after departure is limited by launch energy and by gravity assists. Even at high speed, it takes years to reach the outer planets and decades to reach the heliopause. Therefore, leaving Earth can be fast, but leaving Earth's broader neighborhood in the solar system can be slow. In practice, human missions face additional constraints that further complicate the idea of leaving forever. A human one-way mission to leave Earth and not return would require life support for long durations, and would likely target a destination like Mars or a T habitat rather than the outer solar system. This means the mission timeline would include travel time of months and setup time at destination. The departure from Earth would still occur within hours and days, but the experience of leaving forever would unfold over months. For robotic missions, the experience is different. They can depart quickly and then coast for years, communicating back as they travel. The time is long in the sense of reaching far distances, not in the sense of escaping Earth. The next inward step will therefore focus on the additional energy required to leave the solar system in the gravitational sense and how current spacecraft have approached that, because it provides a grounded comparison between the quick act of leaving Earth and the long act of travelling away from the Sun, and it clarifies what is possible with current propulsion and gravity assists without suggesting that leaving Earth forever requires leaving the Sun. To leave the solar system in the gravitational sense requires more than escaping Earth, and looking at the energy and the examples of existing spacecraft shows how the timescale expands from days to decades once the reference body becomes the Sun. The inward move here is from solar gravity as the next barrier to the specific requirement for solar escape and what has been achieved in practice. In gravitational terms, an object is unbound from the Sun if its total energy relative to the Sun is positive. This corresponds to a heliocentric trajectory that is hyperbolic rather than elliptical. At Earth's distance, the Sun's escape speed is about 42 kilometers per second. Earth already moves at about 30 kilometers per second, which means that an object departing Earth in the direction of Earth's motion can add heliocentric speed efficiently. If a spacecraft could add about 12 kilometers per second in heliocentric speed beyond Earth's orbital speed, it would be at solar escape at Earth's distance. But the spacecraft does not add speed directly in the heliocentric frame. It adds speed relative to Earth, and that speed is limited by launch energy and propulsion. A typical interplanetary departure might add only a few kilometers per second relative to Earth. This is enough to change the heliocentric orbit substantially, but not enough to exceed solar escape. Therefore, most missions remain bound to the Sun. To achieve solar escape with current technology, missions typically use one of two strategies. One is to launch with very high energy using a powerful upper stage to provide a high hyperbolic excess speed relative to Earth, and to direct that speed to maximize heliocentric energy. The other is to use gravity assists, especially from giant planets, to increase heliocentric speed without expending propellant. Gravity assists rely on planetary motion. A spacecraft approaches a planet, passes near it, and leaves with its velocity vector rotated in the planet's frame. In the heliocentric frame, this rotation can increase the spacecraft's speed by borrowing a tiny amount of the planet's orbital energy. The planet's orbit changes by an immeasurably small amount, and the spacecraft's speed can increase by kilometers per second. By selecting approach geometry, mission planners can choose the direction and magnitude of the energy change. The classic examples of probes that have effectively left the solar system's planetary region are the Voyager spacecraft. They use gravity assists at Jupiter and Saturn, and one of them also uses Uranus and Neptune. These assists accelerate them and send them onto trajectories that are effectively unbound from the Sun, or nearly so depending on details. Even for such probes, the time to reach the boundary of the solar wind bubble, the heliopause, is on the order of decades. This is because even at speeds of tens of kilometers per second, the distance is enormous. 1 astronomical unit is the distance from Earth to the Sun, and 100 astronomical units is 100 times that. At a speed of about 17 kilometers per second, travelling 1 astronomical unit takes roughly 100 days. Travelling 100 astronomical units would then take about 30 years, though. Actual trajectories and speeds vary with time. This rough scaling matches the experience of deep space probes. It shows that leaving the solar system's environment is not immediate, even after leaving Earth. Another probe, New Horizons, leaves Earth and then flies by Jupiter for a gravity assist, achieving a high speed that allows it to reach Pluto in under a decade. After the Pluto encounter, it continues outward on a trajectory that will carry it into the outer regions over time. Yet even for such a fast probe, the timescale to reach the heliopause remains measured in decades. This illustrates again that the limiting factor is distance, not the act of escape. The act of escaping Earth is quick. The act of travelling far is long. There is also a subtler question: what does it mean to leave the solar system forever? In gravitational terms, leaving forever means being unbound from the Sun. But an object can be unbound and still travel within the Sun's general neighbourhood for a long time. The Sun's gravitational influence extends indefinitely, though it weakens. A spacecraft on a hyperbolic trajectory still feels the Sun's pull, and its speed relative to the Sun decreases as it climbs outward, approaching its excess speed at infinity. If the excess speed is small, the spacecraft may remain in the general region for a long time, yet it is still leaving. In practical discussion, leaving the solar system is often associated with crossing the heliopause or reaching the distant regions where the density of solar wind drops. This is not a gravitational criterion, it is an environmental one. The heliopause marks the boundary of the Sun's plasma influence, not the boundary of its gravity. Therefore, the question of time depends on which boundary is used. For someone asking about leaving Earth forever, this expansion to solar scale is important because it reveals that the meaning of forever can shift. Forever can mean never returning to Earth, which is satisfied quickly by any heliocentric trajectory that avoids Earth intersection. Forever can mean leaving the Sun's environment, which takes decades even for fast probes. Forever can mean leaving the Sun's gravity, which requires high energy and still leads to long travel times through interstellar space. These layers must be kept distinct. From the standpoint of what is physically required to stop being an Earth satellite, escaping Earth is the decisive step, and it can be achieved quickly. From the standpoint of disappearing into deep space, the travel time is long. Understanding this prevents confusion between leaving and travelling. Current propulsion methods make the leaving step fast, but do not make the travelling step short. Chemical propulsion provides a burst of speed near Earth. After that, most spacecraft coast. Without continuous thrust, their speed is essentially fixed apart from gravitational encounters. Continuous high-thrust propulsion that could maintain acceleration for long periods would change travel times dramatically, but such systems are not currently available for large payloads. Therefore, the practical timescales remain in the range of hours to days for Earth departure and years to decades for deep solar system travel. This reality also sets constraints on the concept of leaving Earth with humans. A human mission that leaves Earth forever is unlikely to aim for solar escape. It would aim for a stable destination such as a planet or moon, or a constructed habitat, because interstellar space offers no place to stop. Therefore, the relevant timescales for human permanent departure would involve months of interplanetary travel and long-term habitation, not decades of outward drift beyond the heliopause. For robotic missions, decades are acceptable. They can travel outward and continue operating for long periods if their power sources and systems remain functional. The examples of existing probes show what is feasible. They also show that leaving Earth forever in the simplest sense is a small part of the full journey. A spacecraft can leave Earth within hours and then spend decades travelling through the solar system. The departure itself is a brief event in the mission timeline. The outward travel is the long quiet phase. The next inward step will focus more directly on the current spacecraft examples as a grounded measure of time, not to list them, but to use them as reference points for how quickly Earth escape occurs and how long it takes to reach major milestones such as the Moon's distance, the region of the giant planets, and the heliopause, because these milestones give concrete meaning to the timescales implied by the physics without turning the discussion into a set of dramatic claims. Existing spacecraft provide a grounded way to understand the timescales of departure, because their trajectories separate the short interval needed to escape Earth from the long interval needed to travel far from Earth and the Sun. The inward move here is from the energy requirement for solar escape to concrete milestones that have been reached in practice. A typical deep space mission begins with a rapid sequence. Launch and ascent to orbit occur within minutes. Departure burn occurs within hours if the mission is designed for prompt injection. After that, the spacecraft coasts guided by gravity and occasional small corrections. In the first day, the spacecraft can move far enough that Earth appears as a small disk rather than a world beneath. In a few days, it can reach distances comparable to the Moon's orbit. These early milestones are within the time frame of ordinary calendar experience. They are also the interval in which leaving Earth forever in the strict dynamical sense is already achieved. Once injection occurs, the spacecraft is unbound or on a trajectory intended to remain away. Yet beyond the first week, the motion becomes a slow drift in human terms because the relevant distances expand quickly. The spacecraft's speed might be several tens of kilometers per second relative to Earth near the beginning, but relative to the Sun, it might be on the order of tens of kilometers per second as well, and those speeds while high are small compared with the distances to the outer solar system. A probe that travels toward Mars typically takes months. This is because the transfer orbit is chosen to minimize energy, not to minimize time. A faster transfer is possible but requires much more launch energy. Therefore, the travel time reflects a trade between speed and mass. Even if leaving Earth is a matter of hours leaving Earth's broader neighborhood, in the sense of being far beyond the inner planets, is a matter of years. A probe traveling toward Jupiter may take about a year or more depending on trajectory. A probe traveling towards Saturn may take longer. These are not strict numbers that apply universally, but the scale is clear. Interplanetary travel is measured in months to years. This scale helps interpret what forever might mean. If forever means never coming back, that condition is met almost immediately after injection, as long as the trajectory does not intersect Earth again. If forever means becoming so distant that Earth is no longer a relevant reference, that may take months or years depending on the chosen threshold. Earth's gravity becomes negligible relative to the Sun's after leaving the Earth-Moon system, which is days, but Earth remains near enough that radio signals are still strong and navigation is still precise. As the spacecraft travels outward, communication delay increases. At 1 astronomical unit, light travel time is about 8 minutes. At 5 astronomical units, it is about 40 minutes. At 10 astronomical units, it is more than an hour. This creates a growing sense of separation not because gravity changes abruptly, but because the simple act of sending and receiving information becomes slower. This is part of what leaving can feel like in an operational sense. Yet the spacecraft is already leaving long before this. Another concrete milestone is passing the orbit of the Moon and then the region near Earth's and Lagrange points. A spacecraft can reach those Lagrange distances in a few weeks if its trajectory is aimed that way, or it can reach them as part of an outward escape in days. Space observatories placed near the Earth-Sun L2 region at about 1.5 million kilometers do not leave Earth forever. They remain in controlled orbits around the Lagrange point and require periodic station keeping. Their travel time from launch to that region is on the order of weeks, which illustrates that deep space location can still be part of Earth-centered operations. This contrasts with interplanetary probes that cross that region on their way out without stopping. The timescale to pass beyond 1 million kilometers on a direct escape is days, but to enter and remain near that region under controlled orbital conditions can take longer due to careful insertion and orbit shaping. This shows again that mission goals shape time more than raw physics does. For probes that aim to leave the planetary region entirely, the timescales stretch. The outer edge of the main planetary region can be thought of as beyond the orbit of Neptune, around 30 astronomical units from the Sun. A probe reaching Neptune takes more than a decade under typical trajectories, especially if it uses gravity assists that shape the path. After passing the giant planets, the probe continues outward into regions populated by distant small bodies. The distance to 100 astronomical units is immense compared with the inner solar system. At speeds of around 15 to 20 kilometers per second, reaching that distance takes decades. This is why the heliopore's crossing times are measured in decades. The probes that have reached such distances provide a clear reference leaving Earth forever is a tiny fraction of their mission time. They leave Earth's gravitational binding quickly, then spend years reaching the outer planets and decades reaching the edge of the solar wind bubble. Even then they remain within the Sun's gravitational influence unless their trajectory is unbound. Yet their path continues outward. This clarifies that the main time component after leaving Earth is simply coasting through vast space. It is not continuous propulsion. It is not a long escape burn. It is a long passage. Another practical dimension is that spacecraft do not travel in straight lines. They follow curved paths determined by gravity and by the need to meet targets. A mission to Mars uses a transfer orbit that intersects Mars at the right time. A mission to Jupiter may use an inner planet flyby first to gain energy which adds time, but reduces required launch energy. A mission that wants high speed outward may use Jupiter as a slingshot. These choices create mission timelines that can vary widely. Therefore, using existing missions as a guide does not mean copying their exact travel times. It means understanding the scale of what is possible with chemical launch plus gravity assists. The scale remains consistent: hours to escape Earth days to leave the Earth-Moon domain, months to reach the nearest planets, years to reach the outer planets, and decades to reach the heliopores. This scale provides a realistic picture of leaving Earth forever, across different interpretations. It also reveals that the word really is less about the physical act of leaving and more about the experience of distance and duration afterward. Many people imagine leaving Earth as a slow climb away. In reality, the climb away from Earth's gravity well is quick, in the sense that the energy change happens in minutes, and the spacecraft becomes unbound within hours. The slow part is the outward drift after the burn, as the spacecraft covers distances that grow from hundreds of thousands of kilometers to millions, then to billions. The engine is not firing most of the time. The spacecraft is quiet and steady with occasional small corrections. This is why the concept of time in deep space differs from time on Earth. There are long coasts and rare decisive events. This is the pattern of interplanetary travel. It is also why leaving Earth forever can be framed as a moment, the injection followed by a long unfolding. If the question is interpreted in human terms as leaving Earth and never returning, the physical part can be quick, but the human part would include the weeks and months in which Earth recedes and the destination approaches. For a one-way human mission, the passage of time would be dominated by life support radiation exposure and the psychology of confinement, not by the escape burn. The physics of leaving Earth would still be compressed into a short interval. The mission experience would not. The next inward step will focus on time versus speed in deep space, because once the engines are off, speed becomes an initial condition rather than a continuously controlled variable. And travel time becomes a simple consequence of distance, and that initial speed with only small corrections and understanding. This clarifies why leaving Earth forever can be fast while the journey away can still be long, and why increasing speed significantly would require fundamentally different propulsion or mission architecture. Once the engines stop firing, deep space travel becomes mostly a matter of coasting, and the time to move away from Earth and the Sun becomes a direct consequence of initial speed and distance, because there is no continuous push and therefore no steady shortening of travel time. The inward move here is from reference milestones to the underlying relationship between speed and time after departure. In the chemical departure regime, most of the acceleration occurs near Earth during launch, and during the departure burn. After that, the spacecraft may perform small correction burns, but these are typically minor compared with the initial injection. The spacecraft's path is then governed by gravity and by the inertia it carries. In the sun-centered frame, the spacecraft follows an orbit determined by its velocity and position at departure, modified by encounters and small maneuvers. In this regime, travel time is largely fixed at the moment the trajectory is chosen. If a mission is planned to reach Mars in several months, that travel time is not an accident. It is the result of choosing a transfer orbit that requires a manageable amount of launch energy. A faster transfer could be chosen, but it would require a higher departure energy, which would reduce payload mass or require a larger launcher. Therefore, time and speed are traded against mass. This trade is fundamental. There is no free way to make travel times dramatically shorter without paying in energy and mass. The same logic applies to leaving Earth forever. If leaving means escaping Earth's gravity, the time can be short because the acceleration is concentrated. But if leaving means becoming far away, time becomes dominated by distance. Earth's distance to the Moon is a few 100,000 kilometers. At a relative speed of a few kilometers per second, that distance is covered in days. Earth's distance to the Sun is 1 astronomical unit, about 150 million kilometers. At tens of kilometers per second, this distance is covered in months. The distance to the outer solar system is billions of kilometers, and at similar speeds it is covered in years. The distance to the heliopause is tens of billions of kilometers, and at similar speeds it is covered in decades. These scales show that the time to travel grows in proportion to distance for a given speed. Because speeds do not increase continuously, the time cannot be shortened by waiting or by hoping for gradual acceleration. It is set by the initial choice of trajectory and propulsion. The coasting phase also reveals why speed near Earth does not translate directly into speed far away. A spacecraft escaping Earth has a high speed near Earth, but as it climbs out of Earth's gravity well, its speed relative to Earth decreases. What remains is the hyperbolic excess speed, which may be only a few kilometers per second. In heliocentric terms, the spacecraft's speed is dominated by Earth's orbital speed plus or minus the departure contribution. Therefore, the outward speed away from the Sun is not simply the Earth escape speed. It is determined by the heliocentric orbit. A spacecraft on an elliptical orbit around the Sun may move faster near perihelion and slower near aphelion. Its radial distance from the Sun changes over time according to orbital mechanics. Therefore, the time to reach a certain distance from the Sun depends on the orbital shape. A spacecraft heading outward might slow as it climbs to a higher orbit. This is similar in spirit to the slowdown relative to Earth during the escape, but now in the Sun's gravity well. This is why reaching the outer solar system takes years, even if the initial heliocentric speed is high. The gravitational field converts kinetic energy into potential energy as the craft climbs outward, reducing speed. The remaining excess speed, if the craft is unbound, is what determines its long-term outward drift. If that excess is modest, decades pass before reaching very large distances. This is the basic reason why the fastest human-made objects still take decades to reach the heliopause and far longer to reach even the nearest stars. Another aspect of coasting is navigation. A spacecraft is not simply thrown and forgotten. Small forces act over long times. Solar radiation pressure exerts a tiny push on the spacecraft, especially on large flat surfaces. Outgassing and thermal effects can create small accelerations. The gravitational pull of planets and small bodies can perturb the path. These forces are usually small, but over months and years they can accumulate. Therefore, mission teams perform tracking and occasional correction burns. These burns are small, but they are crucial for hitting targets. They also illustrate that while the broad travel time is set, the exact path is actively managed. Yet these corrections do not usually change the overall timeline dramatically, because changing arrival time significantly would require a large change in heliocentric energy. Small corrections mostly adjust targeting rather than speed. This means that once a spacecraft is on its way, the time to be far away is largely locked in. In the context of leaving Earth forever, this makes the initial departure choice central. A fast departure that gives a high heliocentric energy can shorten travel times to outer regions, but it requires high launch energy and reduces payload. A slower departure can carry more mass but takes longer. This is the same trade found in all space travel. For human missions, the trade is even sharper, because payload includes life support and shielding. Increasing speed may reduce time and thus reduce exposure, but it increases propulsion demands and thus increases mass. There is therefore an optimum depending on technology and mission constraints. This is one reason why human interplanetary missions are not simply scaled-up versions of robotic probes. Their timelines and propulsion choices are shaped by biology as much as by physics. For robotic probes, long coasts are acceptable, and the mission can be designed around the coasting nature of travel. The probe's power source must last and its communication system must remain functional, but it does not need food, water, or oxygen. This makes decades-long travel feasible. Another part of the time versus speed relationship is that leaving Earth forever can happen quickly, but leaving Earth forever with a permanent change in human life is slow. Even if a one-way mission departs Earth and becomes unbound within hours, the social and logistical process of preparing such a mission could take years. The mission might involve assembling a craft in orbit, transporting supplies and testing systems. The actual travel to a destination might take months. Therefore, the phrase "really take" can be answered in two layers. Physically, the escape state can be reached within hours, and the Earth-Moon boundary can be crossed in days. Operationally and experientially, leaving forever can take months or years, because it includes preparation and transit to a new home. However, within the strict physical framing, coasting explains why the departure is quick and the subsequent distancing is slow. This is also why proposals for faster travel often focus on new propulsion systems that can provide continuous acceleration. If a spacecraft could accelerate continuously at a modest fraction of Earth gravity for weeks or months, travel times to outer planets could be drastically reduced. Yet such propulsion would require enormous energy, high power sources, and thermal management. It is not available for large payloads with current technology. Therefore, present missions remain in the impulsive burn and coast regime. This means that time is controlled primarily by the initial burn magnitude and direction, and by gravitational assist, not by continuous propulsion. Even within current technology, there are modest ways to adjust time. A spacecraft can use a higher energy transfer to shorten travel time at the cost of more propellant or a smaller payload. It can use different flyby sequences. It can use a solar abirth maneuver, diving close to the sun and firing at high speed to gain more heliocentric energy, potentially increasing outbound speed. Such strategies are complex and require heat shielding and precise navigation. They show that travel time can be shortened but not without costs. For leaving Earth forever in the basic sense, such strategies are not required. They are relevant only if the destination is far and if time matters. In most contexts, leaving Earth forever is defined by escaping Earth and not returning. Under that definition, coasting supports a simple answer. The decisive step is quick and the outward separation continues steadily thereafter, with Earth becoming less relevant within days as solar dynamics take over. The next inward step will move from the physics of coasting to the constraints of human biology and life support. Because the phrase "leave Earth forever" often implies a human journey, and for humans the limiting factor is rarely the ability to escape Earth. It is the ability to sustain life and function over the months and years that follow. And those constraints redefine what time means in practice, and why the physical timeline of hours and days is only one part of the full answer. For a human to leave Earth forever, the physical act of escape is only the first hurdle, and the dominant time constraint is shift inward to biology, life support and reliability, because a person cannot simply coast indefinitely without air, water, food, radiation protection, and systems that continue to function. The inward move here is from coasting physics to human limits. A robotic spacecraft can tolerate long travel times if its power and electronics survive. A human cannot. The human body requires a continuous supply of breathable air, drinkable water, and adequate nutrition. It also requires a stable thermal environment and protection from radiation. In space, the absence of atmospheric shielding means exposure to energetic particles from the sun and from outside the solar system. The absence of gravity produces physiological changes. Over weeks and months in microgravity, muscles weaken and bone density decreases. Fluid distribution changes and can affect vision. The cardiovascular system adapts to weightlessness, which becomes a problem when returning to gravity, but even without return, the changes affect long-term health. Therefore, a permanent departure implies either long exposure to microgravity with associated deterioration, or the use of artificial gravity through rotation, which adds engineering complexity and mass. These biological realities change what it means to ask how long it would really take. The time to escape Earth remains hours and days. The time that matters for a human mission is the months and years during which life support must operate without failure. A basic human life support system must control cabin pressure, oxygen level, carbon dioxide removal, humidity and temperature. It must manage waste. It must provide water. It must prevent microbial growth. It must handle trace contaminants. On the International Space Station, these functions are supported by complex systems and by resupply and maintenance. A one-way mission that leaves Earth forever must carry its own redundancy and spares. It must be able to repair failures. It must have a power source and thermal control that lasts for the duration. If the destination is Mars, travel time on common transfer trajectories is months, and then the mission transitions to surface or orbital habitation that may last indefinitely. If the destination is a free space habitat, the mission must either build and provision that habitat first, or carry a habitat large enough to sustain life long term. This implies many launches, assembly and time. Therefore, the time to leave Earth forever for humans is not defined only by the trajectory. It is defined by the overall mission architecture. A human can depart Earth on a one-way trajectory quickly, but without a prepared destination or a sustainable habitat leaving. Forever becomes leaving into a situation that cannot support life for long. This turns the question into one of whether leaving forever is physically survivable rather than merely whether it is dynamically possible. Radiation is a primary driver of this distinction. In low Earth orbit, Earth's magnetic field provides significant shielding, and astronauts spend much of their time inside that protective region. Beyond it, radiation exposure increases. The most variable component comes from solar particle events, bursts of high-energy particles associated with solar activity. These events can deliver large doses over short times, which can be dangerous. A crewed deep space mission therefore requires a storm shelter, a region of the spacecraft with extra shielding where crew can shelter during an event. Shielding adds mass, and mass adds launch complexity. Over longer times, cosmic rays from outside the solar system contribute a steady background dose. Shielding against these is difficult because they are highly penetrating. Therefore, long-duration missions accumulate radiation exposure. This sets practical limits on how long a crew can travel in deep space and how much shielding is needed to reduce risk. If leaving Earth forever implies a long outward journey, with no near-term arrival at a shielded environment, the radiation challenge becomes severe. This is one reason why plausible human permanent departures focus on reaching a destination within months, not years, and on establishing a protected habitat. The biological need for gravity or partial gravity also matters. A one-way mission to Mars would arrive at a world with lower gravity than Earth. The effects of long-term living in lower gravity are not fully known because humans have not lived for years in such conditions. It is known that microgravity causes bone and muscle loss. It is plausible that partial gravity reduces these effects, but the degree is uncertain. Therefore, long-term health outcomes remain uncertain. A habitat with artificial gravity could mitigate this, but building one in deep space requires mass and complexity. Again, the time question is shaped by engineering readiness and mission scale. Another constraint is reliability. A spacecraft leaving Earth forever cannot depend on quick rescue. In low Earth orbit, rescue or emergency return is possible within hours or days. Beyond the Moon, rescue is far more difficult. Therefore, systems must be more robust. Life support must tolerate failures. Power systems must have redundancy. Propulsion must be reliable enough to perform necessary maneuvers. Communication must be maintained. Navigation must be stable. The longer the mission duration, the higher the probability of failure unless redundancy is very high. This is a statistical reality. Therefore, leaving Earth forever implies either keeping mission duration to a manageable time frame to reach a stable destination, or building an architecture with very high redundancy. Both increase cost and complexity. In practical terms for humans, the timeline to leave Earth forever is dominated by preparation. The spacecraft must be built, tested, fueled, and provisioned. If the mission requires assembly in orbit, multiple launches are needed, each with their own schedule. The assembly may take months. Testing may take additional time. Training and simulation may take years. The departure burn itself remains short, but it becomes the final act of a long preparation. After departure, the cruise time to a destination such as Mars may be several months. During that time, the crew experiences confinement, limited privacy, and psychological stress. These factors matter because leaving forever implies that the crew cannot plan for immediate return. The psychological burden of permanent departure would be significant, and it would influence mission design. Larger living volume, better life support, and better communication delay coping strategies all add complexity. Even if the physics allows leaving quickly, the human system does not. The mission must be designed around human tolerances. This also affects the choice of propulsion. Faster transit reduces time exposed to radiation and microgravity, but faster transit requires higher energy and thus more propellant, reducing payload capacity, unless the launch system is larger. This trade is central. It means that leaving Earth forever quickly in terms of total trip time is not simply a matter of choosing to go faster. It is a matter of having the mass and energy budget to do so, while still carrying adequate shielding and life support. For robotic probes, this trade is simpler. They can accept long times and minimal shielding. For humans, it is complex. Therefore, the answer to how long it would really take for humans includes two numbers. The time to escape Earth and cross the Earth-Moon domain is still days. The time to execute a permanent departure that is survivable and sustainable is months to years when preparation and transit are included with the transit itself, likely months for near destinations. A human cannot realistically leave Earth forever by simply escaping and coasting outward indefinitely, because there is no support in interplanetary space. Therefore, leaving forever implies reaching a new environment where life can continue. That environment could be a planetary surface, a base, or a large habitat. Each implies long preparation and long mission duration beyond the escape event. The next inward step will compare permanent departure scenarios more directly separating robotic departures, which can be straightforward, from human one-way departures, which are constrained by biology and by mission logistics, because this comparison clarifies why the phrase "really take" can have a short physical meaning and a much longer practical meaning, and why leaving Earth forever is less about escaping gravity than about sustaining life beyond Earth's protective environment. Permanent departure looks very different for robotic spacecraft and for humans, because a machine can accept long coasting timelines and minimal support, while a human departure requires a destination strategy, a habitat strategy, and a reliability strategy that can keep life going after Earth is gone behind. The inward move here is from human limits to comparing scenarios of leaving forever in practice. A robotic mission that leaves Earth forever can be designed around a simple sequence. A launcher places the spacecraft into a parking orbit or directly onto an escape trajectory. An upper stage provides the departure burn. The spacecraft performs course corrections and proceeds to its target or to deep space. Once it is unbound from Earth and beyond the Earth-Moon system, it is effectively gone. The mission can last years or decades, but the spacecraft does not require consumables in the human sense. It needs power, thermal control, and stable electronics. Its time is limited by component lifetime and by power source, not by air and water. This is why robotic departure is primarily a question of energy and navigation. In that context, the question of how long it takes to leave Earth forever is answered in physical milestones: hours to become unbound, days to leave the Earth-Moon region, and then an open-ended travel time to whatever distance is of interest. For humans, a permanent departure is not simply a trajectory, it is a living system. If leaving Earth forever implies never returning, the mission must ensure that life can continue for the full duration. This means that the departure must be toward a place where life can be supported indefinitely, or at least for a planned long period. In current plausible scenarios, this usually means a destination such as Mars, the Moon, with a permanent base or a free space habitat. Each changes the timeline. A one-way mission to Mars still begins with the same physical steps: launch to orbit, departure burn, escape from Earth, and transit out of the Earth-Moon system in days. But the practical meaning of leaving forever is bound to the months of interplanetary cruise and to the arrival and settlement phase. Travel to Mars under a typical energy-efficient trajectories is measured in months. The departure is quick, the cruise is long. During cruise, life support must run continuously and any failure must be repairable. Radiation exposure accumulates. Microgravity effects accumulate. Therefore, the timeline is constrained by human tolerances. The mission would likely aim for a cruise time that is not excessively long, because longer time increases risk. Yet reducing cruise time requires higher energy and therefore reduces payload mass unless launch capability increases. The payload includes shielding spares and a habitat volume. Therefore, the mission design is a balance. A permanent departure to Mars also requires that the destination can support long-term living. This can involve in situ resource use, such as making oxygen from the Martian atmosphere and extracting water ice if available. These technologies must be proven and reliable. They also require equipment mass. If the mission is truly one way, it cannot depend on Earth resupply. This pushes towards sending cargo in advance. That cargo must arrive and function before crew departure. Therefore, the timeline to leave Earth forever in a meaningful human sense includes pre-deployment missions that may occur years earlier. It includes building a base, stocking it, and verifying it. Only after those steps can a crew depart with a realistic plan to live. In this scenario, the escape from Earth is still a matter of hours and days, but the real timeline to leave forever is years of preparation and months of travel. A permanent departure to a free space habitat has different features. A habitat near Earth, such as a large station, still remains in Earth's gravitational domain, and does not count as leaving Earth forever in a dynamical sense if it stays bound. Yet it could be a permanent home that does not return to the surface. If the phrase leave Earth forever means leave the surface forever, then a habitat in Earth orbit or near Lagrange points could qualify. In that case, the travel time is short, potentially days or weeks. The difficulty is building and provisioning the habitat. This again is a long timeline. The habitat must be assembled from many launches, and it must include closed-loop life support, radiation shielding, and possibly artificial gravity. This could take years. Once built, moving people there could be quick, but the leaving forever is not in the travel. It is in the build. A habitat placed farther away, perhaps in a solar orbit that does not return to Earth, would require additional departure energy and would become a true leave Earth forever trajectory. Yet sustaining life would still require the same systems. The advantage could be continuous solar power and a stable thermal environment, but the disadvantages include distance from Earth support and long communication delay. A one-way departure to such a habitat would again involve long preparation and careful design. Another scenario is a human mission intended to leave Earth without a prepared destination, essentially a voyage outward. In physical terms, this is possible. A spacecraft could escape Earth and enter a heliocentric trajectory. It could continue outward, perhaps with planetary assists, and eventually leave the solar wind bubble. But for humans, the timeline and resource requirements become prohibitive. Food and water for years would require enormous mass unless a closed-loop system with high recycling efficiency is used. Even with recycling, some losses occur and spares are needed. Radiation exposure over years in deep space would be high without heavy shielding. Psychological and social factors would be severe. Without a destination, the mission becomes a drifting life support problem. Therefore, while the physics of leaving Earth forever is straightforward, a human voyage without destination is not a realistic near-term scenario. This highlights the difference between leaving Earth in a dynamical sense and leaving Earth as a place to live. Human departure must be anchored to habitability, not to distance. The question of time also changes depending on what forever means. If forever means never being gravitationally bound to Earth again, a human mission can satisfy that in hours if it departs on an escape trajectory. But the crew will still be alive for years, and the mission must support that. Therefore, the meaningful time is the time to reach a stable living environment, which is months for Mars, and potentially weeks for a near-Earth habitat if it already exists. If forever means leaving Earth in a cultural sense, abandoning Earth as home, the time is measured in decades of infrastructure development. None of these changes the physical timeline of escape, but they dominate the real-world meaning. Even for robotic missions, the practical timeline can include years of development, but the question here focuses on the travel and escape time. For robotics, the answer remains compact. For humans, the answer is layered. There is also the scenario of a one-way mission to the Moon. This does not leave Earth's solar neighborhood, but it leaves Earth's surface. A lunar base can be supplied more easily than Mars because travel time is days and communication delay is seconds. If a person leaves Earth to live on the Moon permanently, the travel time is days and the life support and radiation challenges remain but are different because the Moon is near. This is another way to interpret leaving Earth forever. It emphasizes leaving the surface rather than leaving Earth's gravity. Under that interpretation, the time is short in travel but long in preparation. A final practical point is that leaving Earth forever involves legal and social systems, not only physics. These do not determine travel time, but they influence feasibility and planning. For the script's purposes, the main lesson remains that travel time is not the limiting factor for leaving Earth forever. The limiting factor for humans is the ability to sustain life. For robots, the limiting factor is launch energy and mission planning. In both cases, the physical timeline of escape is short compared with the rest of the mission. The next inward and final step will clarify what forever means in practice, emphasizing that leaving Earth is a sequence of thresholds rather than a single moment, and it will settle the answer into a calm description of the ranges: minutes to orbit, hours to escape energy, days to leave the Earth-Moon system, and much longer times for the mission goals that make leaving meaningful, followed by a wind down that holds these ideas gently, without turning them into a dramatic conclusion. Forever is not a single distance, and leaving is not a single moment. And the most realistic answer is a calm sequence of thresholds that show how quickly Earth can be escaped, and how slowly distance accumulates afterward. The inward move here is from contrasting scenarios to the practical meaning of the word forever. In the strictest dynamical sense, leaving Earth forever means becoming unbound from Earth, meaning that the spacecraft's trajectory relative to Earth is open and will not return unless new propulsion is applied. Under common chemical launch and injection patterns, this can happen within hours of liftoff. The vehicle rises to orbit in minutes, coasts as needed, and performs a departure burn that raises its energy above the escape threshold. At that point, Earth is no longer the central body that can keep it in a repeating orbit. The spacecraft still remains physically near Earth for some time, but the status has changed. In that narrow sense, the time to leave Earth forever can be surprisingly short. Not because the distance is small, but because the transition is an energy condition that can be met quickly with high thrust. A second threshold is leaving the Earth-Moon system in a practical dynamical sense, meaning reaching distances where Earth's gravity is no longer the dominant guide and the spacecraft is best described as a sun-orbiting object. This occurs on the scale of the Hill sphere or similar regions at distances of about 1 million kilometers. For typical interplanetary departures, reaching this regime takes days. The exact number depends on departure energy and trajectory, and it can be longer for low-energy or low-thrust missions, but the scale remains days for the common case. This threshold corresponds to an operational shift as well. Navigation and planning move from Earth-centered to heliocentric. Communication delays grow, and the spacecraft is no longer part of near-Earth space. In many everyday interpretations, this is what leaving Earth feels like, because it is beyond the Moon and beyond the region where Earth dominates. Therefore, if the question is how long it really takes to leave Earth in the sense of leaving Earth's system, the answer is still not long on a cosmic scale. It is days. A third threshold is leaving Earth forever, in the sense of never encountering Earth again. This depends on the heliocentric orbit. A spacecraft can escape Earth and still remain on an orbit around the Sun that crosses Earth's orbit, potentially creating future encounters. Many trajectories are designed to avoid this either, because they go to another planet, change inclination, or move to a different orbital radius. In those cases, the condition of never returning can be satisfied as soon as the departure trajectory is set. The time is then again tied to the departure burn hours after launch. Yet the word forever can also mean something broader: the time until Earth becomes physically small, emotionally distant, and operationally irrelevant. That sense is not defined by escape conditions. It is defined by travel through distance. In that sense, the time extends. In a few days, Earth is already far behind at lunar scales. In a few weeks, the spacecraft can be millions of kilometers away. In a few months, it can be well into interplanetary space on the way to a destination like Mars. In years, it can reach the outer planets. In decades, it can approach the edge of the solar wind bubble. These are not statements of what is required to leave Earth. They are statements of what happens after leaving because the spacecraft coasts. It is in this coasting phase that time accumulates. The spacecraft separation from Earth becomes a quiet arithmetic of distance divided by speed with gravitational fields shaping the path. For robots, this quiet arithmetic is the main part of the mission. For humans, it is the part that must be survivable. For a human mission forever implies a commitment to living beyond Earth's surface. Under that interpretation, the key threshold is not Earth escape, but reaching a stable living environment. If that environment is a near-Earth habitat, travel time can be days or weeks, but the habitat must exist first. If the environment is the Moon, travel time is days. If the environment is Mars, travel time is months. In each case, preparation dominates. Hardware must be built, tested, and provisioned. Cargo may be sent ahead. Systems must be reliable. Life support must function. Radiation protection must be sufficient. Therefore, for humans, the time to leave Earth forever is best understood as years of preparation plus months of transit, even though the physical escape from Earth can still happen within hours and days once the launch occurs. The difference between these answers is not inconsistency. It is the difference between a dynamical definition and a lived definition. The question asks how long it would really take. The real answer therefore includes both the short physical threshold and the long practical unfolding. In physical terms, a spacecraft can stop being Earth-bound within hours and stop being Earth-dominated within days. In practical terms, leaving Earth forever as a life choice implies long preparation and reaching a destination where life can continue, which adds months and years. The phrase forever also contains an implicit asymmetry. Returning to Earth is easier than leaving Earth in some respects, because Earth is large and easy to find. A spacecraft on a heliocentric orbit can in principle be redirected, but only if it has propulsion and if timing allows. Many spacecraft do not carry enough propellant for such a reversal. Therefore, for many missions, the point of no return is soon after departure, when the spacecraft has committed to a trajectory and has limited propellant left. For humans, a one-way mission would similarly pass a point beyond which return is no longer feasible with available resources. That point could occur within days after a lunar flyby, or after interplanetary injection, depending on architecture. This again emphasizes that leaving is a sequence. There is the launch, the orbit insertion, the departure burn, the crossing of the Moon's distance, the crossing of the Hill sphere, and then the long coasting outward. Each is a threshold with its own timescale. In calm summary within the constraints here, minutes carry a spacecraft from the pad into space. Hours carry it from orbit into escape energy if the mission is designed for it. Days carry it out beyond the Earth-Moon system so that the Sun becomes the main reference. From there, months and years carry it to destinations that make leaving meaningful. The word really take is answered by choosing which threshold matters. If the question is about the physics of no longer being able to fall back to Earth under gravity alone, the answer is hours. If the question is about no longer being in Earth's gravitational neighborhood, the answer is days. If the question is about leaving Earth as home and living elsewhere, the answer is months to reach near destinations and years to prepare. The wind down begins as the idea of threshold settles into stillness. The Earth is a strong gravity well with a thin resisting atmosphere, and leaving it demands a concentrated burst of energy. That burst can be delivered quickly, and the decisive transition can occur soon after launch. After that, the spacecraft drifts outward, passing the Moon's distance, then passing the broader boundary where Earth's pull is no longer the main guide. The outward motion continues under the Sun's gravity, and time stretches as distances stretch. For robots, the long quiet travel is routine. For humans, the long quiet travel is the problem, not because leaving is hard in hours and days, but because living is hard for months and years. The practical meaning of leaving Earth forever becomes a question of where life is sustained, how systems endure, and how the slow passage of distance is managed. The physical answer stays simple and bounded. The rest is the unfolding of a journey that becomes longer the farther it is asked to go.